All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this time we have just to study your creation. Just help us use this time wisely and to get lots of problems solved, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's do number 39 from chapter 28. I hope I haven't done this already. If I have, you stop me. All right. So this is a particular example of Ampere's law. And so the deal is you got a solid conductor with radius A supported by insulating discs on the axis of a conducting tube with inner radius B and outer radius C. All right. And, oh, interesting. All right, well, let's work on this here. So we've got radius A here, right? And then I'll try to make it bigger. So then, let's see here. This is radius B, and then radius C to the outside, right? All right. And so let's see here. I'll draw another picture. So too many things to draw. The point, though, is that there's a current so there's two currents in this situation, right? The one current is in the inner conductor, and it's going like this, right? But there's an equal current on the outer conductor going like that, right? So let me shade the conductors for a second here. So this conductor here, right? And I'll do a different color for the other one. That, right? So the blue one, the current's going to the left on my picture, whereas the purple one, the outside conductor, is going to the right. So it's a coaxial cable. The question, and the currents are uniformly distributed over the cross sections of each conductor. We were asked to derive an expression for the magnetic field in a couple different cases, I think. At points outside the central solid conductor, but inside the tube. And also, oh, this is an easy problem. Oh man, why did I do this one? It's only got one blue dot. This won't make me feel better about my day at all. This is like, I don't know, it's just like going to a schoolyard and like beating up a small child or something, this problem, you know? Not that you should, gain satisfaction from beating up little children. Obviously, but like this is not a bully or anything. So the question's really nice because they only ask us for the magnetic field where it's obvious. Like I don't need to write anything down. I can just write answers down for this problem. So they ask us to find, basically, they ask what's the magnetic field in here, in that case, right? And they ask us also what's the magnetic field out here in this case, So for R greater than C and for R between A and B, all right? So those are really easy to figure out. So first of all, like there's a cylindrical symmetry, right? Like we have that. Let me check my mic. If I turn my mic back on. If I notice my mic is off an hour from now, it would be really annoying. But it's working. Woo-hoo. Okay, so let's just apply Ampere's law, right? So imagine, I'm just going to draw it in my two-dimensional picture because it's easier, right? So if I make my Amperian loop like right here, right? Then the current, let's say the current's coming out at me, okay? Then the magnetic field lines, they wrap around there like that, right? Those are my B field lines. And so in case A, come on. We have, you know, the line integral of B dot dl over the loop, right, is equal to, you know, mu naught times the current enclosed. But what is the current enclosed? So we've got B times 2 pi r is mu naught. Well, the current enclosed is the whole thing, right? I mean, it's kind of silly, this question, because it's just, you got the whole inner current I, so it's just mu naught I, you know? So therefore B is simply mu naught I over 2 pi r, you know, for B less than R less than C, A less than R less than B, rather. All right? And then for part B, it's even sillier, because what happens with part B if you have an Empyrean loop that's out here, that's supposed to be a symmetric circle about, these are all supposed to be circles that are exactly symmetrical about the axis, right? So again, Ampere's law would give us B times 2 pi r from the circulation of the magnetic field is mu naught times the current enclosed, right? But what is the current enclosed? Well, you got the blue current in the middle, right, coming out at you. So that's I. But we've also got the purple here, right, going into the board in my picture. See? And it's uniformly distributed, which is why we've got this nice cylindrical symmetry. So that is going, so the blue's coming out at us, the purple's going in, but it's the same magnitude current. So that gives you minus I, because they're going opposite directions, right? So so that's 0. So therefore, the magnetic field is equal to 0 for R greater than C. Yeah. Yeah.
What's the surface area?
Mm-mm. Mm-mm. I don't think so here. So this is 39, right? So we can check our answers, you know. Did you? Oh, you're working on it? I would be shocked if we were wrong. Okay. Oh, good. I did something right today. All right. So to make this problem more interesting, what I thought this problem was when we started it, I thought they were going to ask us for what's the magnetic field like in the blue. See, that's slightly more interesting. So how would we do that? If I was to draw a little Amperian loop in there, I'll make it orange, right? Like in here, you'd have, again, you have the symmetry because it's a uniform current. So you still have the magnetic field times 2 pi r, that's the circulation of the magnetic field, mu naught times the current enclosed, right? But what is the current enclosed? Well, it is the fraction of the area inside the orange loop, which would be pi r squared, right? Divided by what? What's the whole area of the inner conductor? Well, just pi a squared, right? And that, of course, times I. So that gives you the fraction of the current which is enclosed by the Amperian loop, which, of course, then tells us that the magnetic field is, you know, the pi's, they be canceling, and we get mu naught I r divided by 2 pi a squared, I think. So I'm just solving for b. And that's for 0 less than or equal to r less than or equal to a. And then I think actually this is a very interesting problem if you actually work it all out. They should have asked you also, part D, they should have asked you what's the magnetic field in the outer conductor, right? That's actually very interesting. So, you know, if I was to make a Amperian loop, I'll make it green this time, like here, right? Inside that, right? Again, by the cylindrical symmetry, the circulation, the line integral of the b dot dl is still b times 2 pi r. But now, the current enclosed is a little bit tricky. In fact, it's a lot tricky. It's trickier than anything I've worked in class. See, because, all right, so what's the current enclosed by the green loop? You've got the current coming out of the board at us, which we're counting as positive, and it's all enclosed, so it's the whole current I, right? But then we have minus the fraction of the area of the outer, right? So what is the, so if I was to hash it, you know, well, let me not, but if I was to shade this all in, like what area is that? Well, that's what? That's pi r squared minus pi, what's that? B, right? B is the inner radius of the outer thing. So pi r squared minus pi b squared divided by, you know, I'm trying to find the fraction of the area because that's going to give me the proportion of the current that's flowing in that through that loop. So that's the area inside the green loop as part of the purple shaded region. So I need to divide by what? Pi, the total area, which would be what? Pi c squared minus pi b squared, right? And that all gets multiplied times I. So you see how this works? When we get to r equals to c, when you get to r equals to c, this becomes 1. I minus I is 0. See, because once you get to the edge, the net current enclosed is 0. But it should kind of go from I, it's I when r is equal to b, and it drops to 0 as you go on, you go out past, you know, from b to c. So we can simplify this a bit, right? That's mu naught times, you know, like 1 minus r squared minus b squared over c squared minus b squared. Cancel all the pi's out, and I factor the I out like that. I mean, why not? And so the magnetic field is equal to mu naught times that mess, which we could make into a single fraction, but I just don't care to do that algebra at the moment, so forgive me. 2 pi r. And this would be for b less than or equal to r less than or equal to c. So the book didn't ask us for this one or for this one, but in fact these are very nice test questions, which I've asked before. I don't usually ask all of this all at once, but like asking for just the middle case is something I've definitely have done. Wouldn't be surprised to find it. But this is actually very interesting. If you graph the whole thing, like what's happening, like let's look at a graph of all this. So if we draw the magnetic field, right, versus radius, we start at 0, right? We start at 0, and what happens? Linearly increases up to this value right here at radius A, right? At radius A, it's as big as it gets, I think, which is mu naught I over 2 pi A, right? Mu naught I over 2 pi A is that value. And then it reciprocally reduces, right, like that, until you're to radius B, right? And then what happens? So in the case of the inside, it was pretty easy to understand the graph, right? Because if you look at this formula, it's just a constant times r, right? That's a line with slope mu naught I over 2 pi a squared, right? This formula here, it's not linear. It's something kind of more nefarious, but whatever it is, it's some kind of curve, right? I don't know what it looks like offhand, but we do know that by the time you get to C, the magnetic field is what? 0. So it's got to look something more or less like that. So if you wanted to calculate the if you wanted to calculate the energy stored in the magnetic field, you'd have to like integrate with respect to r over this thing of d squared over 2 mu naught. Assuming that the permeability between the conductors are, well, anyway, there's a lot of assumptions there. I don't think if I know what's good for me, I want to sign that. Because no one wants to square this and integrate it, especially symbolically. Let us move along. Let's see here. Let's try number 61, 82861. That might be good for us to try. Then we're going to go over to the 29. Did I do this one already? I don't think I have. All right, so what you got, and I'm going to draw this a slightly different way. I'm going to draw it sort of like, here's the top that the things are hung from, and rather than drawing two connections, I'm just going to draw like one connection to start with, like this, right? Because we're given that the angle off the vertical, right, is 6 degrees on both sides, yeah? And we're also given that the length is 4 centimeters. I think that's true for both sides, right? And I'm going to draw this one as going into the board, and I'm going to draw this one as coming out of the board. All right? So if we do that, so the picture in the book draws it kind of in three-dimensional perspective, right? Which is nice. But this has all of the information that the book's picture does, but I think in a kind of more analytical fashion, right? I prefer two-dimensional pictures that have the relation between the things more clearly laid out. And like that's what this plus and that notation gives us much better diagrams for the purpose of calculation sometimes. All right, so what's the problem say? It says 2 long parallel wires hang 4 centimeter long cords from a common hang by 4 centimeter long cords from a common axis. The wires have mass per unit length. Ooh, interesting. So mass per unit length of what is it? 0.013 kilograms per meter. Great. And they carry the same current in opposite directions. What's the current in each wire if the cords hang at an angle of 6 degrees with the vertical? Oh, that's it, huh? Cool. So what's going on here? Why are they not just hanging straight down? Like, what's keeping them from just... Obviously, this problem is assuming gravity, right? So in both of these, we'll just, we can focus on whichever one we like. I'm going to focus on the right one, like that. So this is mg, right? And we're going to focus on, we're going to let m equal to, like, you know, delta m, delta L, you know, times a specific length L, let's say. You know, I mean, what I'm trying to say is that is the mass for a given length L. We're going to analyze, since they're very long lines, we can, by symmetry, just focus on a particular length L and study that. If you want to, you could assume L is equal to 1 meter and work it out like that. But I usually use symbolic ones just to be less, you know, well, it just violates my taste and sensibilities to use 1 meter. But anyway, and also that would confuse the students less, so instead I use L. But anyway, if that's the force of gravity, right, why is there a force here at all? So if let me call this one, we'll call this one, you know, this is 1, this is 2, right? So the current 1, the first current, right, it's going into the board, right? So the magnetic field from that does what? When it comes over here, this is the direction of the magnetic field, right? The magnetic field from current from 1 is that. This is, you know, due to the current, right? Like that. Okay, great. Now, what direction does the force go? Remember, the force on 2 here, the force is what? The force on 2 is, let's see here, I'll say L vector across, which B? Well, B1, right? So the L vector points in the direction which this current's going, which is, it's coming out at us, right? So current L's going like this, right? And I cross into B1 like that, straight horizontal, right? So this force right here is the force on 2 I was just mentioning. Right? What else? So this takes us back a minute, right? Back to last semester. What else? I mean, so this is in equilibrium, right? So the sum of the forces on the mass, that, you know, that length L segment is 0. What else is keeping it there? Why doesn't it just go down like this? What's the other force at play here that leads to equilibrium? This is going to be a blast from the past, but tension, right? The tension force is right there, right? So we have, you know, the sum of the tension force, the gravity force, and the electric force is 0 there. And so let's see here. What's the x component of tension? So like the x component of tension is what? It's like minus, you know, the tension, whatever it is, right? Times what? sine of 6 degrees, I think. Do you see the triangle here? So the x component's the opposite side relative to the 6 degrees. So I get sine 6 degrees. On the other hand, the y component of the tension is upward, and it's t times the cosine of 6 degrees. Right? So we got that. Great. And apparently, we should expect what? In terms of x, like we can just break these equations down into components. That's what I would do. So I need that the t times the sine of 6 degrees, that must balance out. That must be equal to this one right here, right? ILB. B1. And I can drop the cross product because they're perpendicular vectors, the B1 and the L, right? Okay. And I can be more specific here too, right? So we're talking about I, L. What is the magnitude of B? Remember, B1 is mu naught I over 2 pi R, right? What is R? R is the distance from the source current to the field point. So in this context, this distance right here is my R, right? So what do we got? We got ourselves a, mu naught IL squared. How did I get the L squared? What's wrong with me? I squared. Mu naught Li squared divided by 2 pi. Can you tell me R? That's why we need the 4 centimeters, right? R should be what? It's twice. Well, R over tangent of 6 degrees is tangent of 6 degrees should be R over 2 divided by. Oh, I'm a dummy. I don't want to use tangent. What should I use? How about sine, right? Sine of 6 degrees is equal to R over 2 divided by 4 centimeters. So you can solve that. We get the R we're interested in is 2 times the sine of, come on, 2 times the sine of 6 degrees times 4 centimeters, right? It probably would be wise to work a number out there. I wonder if I brought my calculator today. I do. Woohoo. I've got it. All right, so 2 times the sine. Am I in degrees? That's good. Times 4. I've got point. I got a point. Ah, come on. Ow. Stupid finger's not working. R is approximately 0.83623 centimeters. Great, so we know what R is now. But we don't know the tension, right? So, and we don't know the current, right? So we don't know tension, we don't know current, we know mu naught. L is gonna, that's gonna balance out. Okay, so how about the y component? So in the y component, we've got, apparently t times the cosine of 6 should be equal to what? It better balance out the mg, right? But of course, mg, we should really write as, the 0.013 kilograms per meter times what? Times my hypothetical length L, right? And then of course times G. was the question?
What is the current?
Oh, it's the current. Okay, okay. So at this point we're done, kind of. Because what you do, right, is solve this guy, right? Solve for t. And then take that, put it up here, then look at what you have. You have an equation that just involves the current squared and things you know. So let's see here. So we get t equals to 0.013 kilograms per meter times Lg divided by cosine of 6 degrees. Plug that in, we get I guess I'd put it up here. That'd probably be a good idea. That's going to give us, up here, I'll put it up here. Notice that the sine over cosine gives me a tangent. So I'm going to get like 0.013 kilograms per meter. My handwriting's worse up here. Times g times L times the tangent of 6 degrees. That's what I get over there. Equals to mu naught L I squared. Of course, the L cancels out, right? You see that? That's not that should have that has to happen because the L is just the sample length we're analyzing. So see the L's they cancel, yeah. This one and this one they cancel, and lo and behold, we get the current is equal to 0.013 kilograms per meter times 9.8 meters per second squared. Next year I'm changing that to 10 meters. I'm telling you what, next physics, 10 meters per second squared. See, what do you think? Is that going to improve the scores? I feel like it might improve the scores. It might. I mean, it's not right, but you know, we'll just say the Earth got fatter or something. Let's see here. So G, the L's canceled. We've got a tangent of 6 degrees, right? We still got to multiply by 2 pi. And then the R we figured out over there was our 0. I'm going to put it back. I need to put it into meters. Let's go ahead and do that. 0.0083623 meters. I think that's it for my things in the numerator, and I need to divide all that mess, right, by mu naught. Now mu naught is 4 pi times 10 to the minus 7th, right? And anyway, units. I always forget the stupid units for mu naught. What are the units? What is it? Oh, you got it?
Newtons over
Newtons over what? I mean, we've got that equation, B is equal to mu naught over 4 pi, like dl cross r hat over r squared, is it? No, there's an I. I'm missing I, mu naught I. So, I don't know. We just worked it out at last class. I'm very bored. Newtons over amp squared?
yes.
Huh.
Tesla meters over amps.
Tesla meters, I'll go with Tesla meters over amps. Okay. Anyway, what's going to happen?
Square root that?
Yeah. So, yes, we're not there yet, but yes. Mu naught, and that's it, right? So then we square root of all that. Tell you what, just for the sake of being correct, I'm gonna watch this. It's a pro tip. When in doubt, amps. I mean, it has to work out like this. All right. Here we go. 0.013 times 9.8 times tangent of 6 times 0.0083623. All right. And then I will divide by 2. And then I will, I cancel the pi's out. Multiply by 10 to the 7th, because dividing by, same as multiplying. I get 559.86 before I take the square root. After I take the square root, I got 23.66 amps. Please let that be the answer. Okay, so we're either both right or both wrong. 23.2? Okay, so well within the, they probably just, as you know, I'm incapable of minding significant figures, but the textbook is a little bit more meticulous on that point. So we'll chalk it up to sig figs. Cool. All right. Let us forge ahead into chapter 29.
Actually, I forgot that my number was different for my last grader, so it actually might be. In my book, it's 0.0125.
Oh, you got a different one?
Yeah.
So they're different problems. Slightly different problems. My 28.61 answer is allegedly 23.7. Yeah.
Since mine was different.
Ah, okay, so it's actually a slightly different problem. I hate it when they do that. Honestly, like, it's really annoying. Okay, so let's try to do some Faraday's law. Notice that, like, if you read the section, and you guys will definitely gain much by reading the book. You know, like, my notes are not as expansive as, like, my Physics 1 notes are pretty. There's a fair amount there. There's less in my Physics 2 notes in their current form. So you definitely gain something by just reading the book. You know, I try to explain things in class, but I miss things. And there's definitely more real world, you know, phenomenological explanation in the book, which I think is kind of important for your just general knowledge. So you know, a lot of that stuff you really should read just for the sake of educating yourself. And, you know, you guys are mostly engineers, so people are going to rely on you to understand physics and apply it, you know. So it's in your best interest to read the book, even if it doesn't directly pay off on my tests or anything like that, you know. So anyway, my point was, if you read the section on motional EMF, we worked like the sliding bar problem, right? But if you look at the picture, figure 29.15, a conducting rod moving in a uniform magnetic field, you also generate a voltage from just having a conductor moving through a field, you know, a magnetic field. Even if there's no bar or anything, if you just have, you know, a magnetic field like this, right? What's argued there is if you have a conducting bar and it moves through such a field, right? Like this, you know. Then what happens is the electrons are pushed, right? It says the charges in the moving rod are acted upon by the magnetic force FB. So if you think about this, right? If you got a little charge in here, right? What happens if the magnetic field pictured, right, in the blue at the moment? So it's going into the board, right? So if Q is a positive charge, what happens? This whole bar is moving to the side like that, right? So remember the magnetic force, the Lorentz force, QV cross B, right? Keep that in mind, right? So I got V, I cross it into B. So you see I've got on a positive charge, I got force like that. So what happens is you're going to get sort of positive charges up here, right? And if you had negative charges, they'd go down here. So there's a polarization that happens from the magnetic field acting on the charges in the conducting bar, right? And it turns out that you can quantify that by the voltage, like basically the voltage from here. So like the voltage in the bar is equal to the velocity times the magnetic field times the length. So I'm supposing that the length of the bar is L. All right. We came to the same result for the sliding bar, but it works out the same here for this. And so, for instance, for an example, a pretty like standard test question that's based on this, you might say you have a jet airliner, right? And it's going through a cloud, in a thunderstorm where the magnetic field happens to be a certain amount. What's the voltage that's, developed from wingtip to wingtip? You could imagine that's a plane and it's going through a place in the sky where you have that magnetic field, right? Like for example, maybe your magnetic field is 0.03 Teslas. Your velocity is, I don't know. I will spare us the unit, to make this fun, of course, you give it in miles per hour, so you guys have to convert to meters per second. We'll skip that. We're just going to say, we're just going to assume the velocity is, let's pretend something could go 500 meters per second. That's pretty fast, I think. I'm not sure that's actually possible for a current commercial. Well, anyway, I have no intuition for meters per second whatsoever, Anyway, so velocity of 500 meters per second, and what's the typical wingspan? Maybe we could say, I don't know, 30 meters or something. What would the motional EMF, this is called motional EMF. What would the motional EMF be induced then in this situation? Well, you'd have a voltage of 500 meters per second times your 0.03 Teslas times your 30 meters, and that would give you the voltage. So in this silly made-up example that I have here, we've got 500 times 0.03 times 30. I get 450 volts in this situation. All right. So that's, that's something.
Where was the equation from? Did we do that in class?
No, this is a close cousin to the sliding bar problem, but this is generally true. So this is equation 29.6 in the textbook, equation 29.6. It's not in my notes. All right, but I will probably try to impress upon the students that I care about it by suggesting some of the recommended homework problem on this. And the fact I'm talking to you about it right now, So, all right, so let's see if we can find a problem that's based on this you know. And then we'll work some Faraday's law problems because we should do that, okay? So it's like 2925 is one of these. 2925 is such a problem. (2925). Here we have a conducting rod. The length of the conducting rod is given to be 30 centimeters. And its in the magnetic field in play is 0.45 Teslas. And it's directed into the plane of the figure, and the velocity of the rod is 5.0 meters per second. All right. And it says, what's the potential difference between the ends of the rod? And then it asks the question, which point, A or B, is at the higher potential? All right, so let's think through this. So part A is really easy, right? So like A is just the voltage, in terms of magnitude, is just VBL, right? And so we multiply those, you know. Be careful, 30 centimeters is 0.3 meters, right? So whatever that works out to. I'll not try to do that in my head. 0.3. So we get, what, 0.675 volts? Ooh, did I ever move the camera over there? Did I ever move it back? Where is it right now? Well, it's over here right now. I think I was over here before. I really hope so, because I think that explanation was pretty decent. But it would just be right on brand for me to have not moved the camera over today. Anyway, at the 48-minute mark, the complete solution is shown. Let us remember that. I'll make a comment. All right, going back. Okay, so we got 0.675 volts. Now, this is kind of a funny one, right? So they got the magnetic field like this, right? And the bar is like 45 degrees, like this, right? So the velocity is going like this, yeah? All right. So we need to figure out the polarity of the induced voltage here, okay? So we got to think through this. This is a new thing to think about, all right? But let's figure it out. So the question is, which point, A or B, is at the higher potential, right? Yeah, there's 0.675 volts between the points, right? Here's point A, here's point B, but which is at the higher potential? So before we look at that question, let's look at a more basic question. This just a quick review, right? If I have an electric field that goes like this, right? If that's my electric field, right? Is this point A or is this point B at a higher voltage? How are voltage and the electric field related? Do you remember? Like mathematically, it's minus the gradient of the voltage, right? So what this equation means is that the electric field points towards the direction in which the voltage is lowering. The gradient of V always tells you exactly the direction you should go to increase the voltage fastest. That's like the mathematics here. So, or thinking of it physically if you like, electric field lines, they will push positive charges to a state of lower potential energy. So nature always tries to lower potential energy in this kind of situation. And so that would mean that A is at a higher potential and B is at a lower potential. So pretty much if all of your positive charges are going, like in my previous thing right here, since all of my positive charges are getting shoved up there, that shows me that like the induced electric field was like that, which would tell me that lower voltage, higher voltage in that situation. Okay? So now we need to do the same analysis over here. If we think about a little positive charge in here, where does it get pushed? All right, so let's think about it. V, right? V crossed into B. B is into, B is what? Into the board? B is into the board, right? Okay, so V, yowzers, my wrist doesn't do this. Cross into B, okay, so up that way. So we're gonna get the positive charges up here and the negative charges down there, which says that, therefore, A is at the blank potential, higher or lower? Higher, right. All right. Is there any more to this question? Oh, goodness gracious. How many parts are there to this thing? No, I've had enough. I've had enough. There's two parts to part E. Oh. All right, well, I'm going to leave the rest of that to you guys. Let's see here. What was this, 29, 25? Let's make sure at least I haven't steered you wrong here. 29, 25. 0.675 volts. Woohoo! B is B. But what was the question? Which point A or B is at the higher potential? B, it says B is at the higher potential? Oh man, really? Oh, did I do something wrong? Where's the velocity? It says pictured. Did I put the labels on right? A and B. V cross B. V crossed into B. No, V. V crossed. Yeah, V crossed up that way. So that. I am confused. Am I misreading it? Which point A or B is at the higher potential? Higher potential. Higher potential. I think A is at the higher potential. Because, golly. All right. Let me check. So they've got the magnitude. Let's see. If you read page 993, from the above discussion, E equals to VB. So VAB is equal to VBL, with point A at higher potential than point B. Oh, I have somehow golly, really? All right, well, the book says it's backwards of what I'm thinking. The moving rod has a source of EMF with a charge moves from the lower to the higher potential. Charge moves from the lower to the higher potential. We call this EMF motional EMF. Huh. Oh. All right, well, anyway, it's exactly backwards of what I told you. I'm sorry, I don't know how to... Sorry. Well, odds of me testing on that are pretty low. Okay, so that would be pretty lousy for me to test on that, given that I've given you a very possibly convincing wrong explanation. So I will test on the magnitude, but perhaps not the direction of the polarity. But if we believe the book, it's exactly the opposite of what I said, which means I'm thinking of the electric field wrong somehow. Maybe it's well, let me not speculate. Let's go on. Let's work some Faraday problems. Let's redeem the time here. All right. Did we do any of the 29 ones yet?
I don't think so.
Okay, cool. Then we can't go wrong. Oops. Here we go. We'll start with number 1. Can't go wrong there, right? Number 29.1. A single loop of wire with an area. The area is 0.9 meters squared. Is in a uniform magnetic field that initially has a value of 3.8 Teslas, and it is perpendicular to the plane of the loop, so normal to loop. In other words, it counts, you know. And then it's decreasing dB dt. The decreasing rate of the magnetic field is 0.19 Teslas per second, and that's a decrease, so we'll put a minus there, right? What is the EMF induced in the loop? And if the loop has a resistance of 0.6 ohm, find the current induced. All right. Well, this is pretty cut and dried, right? So like the magnetic flux here, right, is simply equal to B naught times A, right? Well, B times A, let's say. The initial amount doesn't matter a bit. That's completely immaterial to the problem. It's just to mess with you. And since the area of the loop is not changing, the derivative with respect to time, right? And this is Faraday's law, says that the voltage induced is minus d phi b dt, right? And that's just going to be what? Minus A, well, I'll write it out, minus d dt of what was it? Well, BA, right? But A is constant, so we can pull it out of the derivative, and we just have what? We've got minus dB dt times A. But those are both given, you know? And so what we have is 0.19 Teslas per second times the area, which was 0.09 meters squared.